In this video of finding electric field due to continuous charge distribution, we shall calculate electric field at a point x away from a disk of radius r having charge q. So consider a disk of radius capital R having charge q uniformly distributed over it, and we shall find electric field at this point situated at a distance x from the center of the disk. There are three simple steps to solve bodies of continuous charge distribution. The first step being select a tiny element. So on any given object, select one tiny element, find electric field due to only that element, and then integrate for the whole body. Depending on the shape and size of the body, the limits for integration will vary. So in this case, since we have the disk, we shall select the tiny element as a ring. We have already derived an expression for ring. The link for that video is available in the description. Now this ring will have radius small r having charge dq distributed over it and has a thickness of dr. Here, any point on the ring of radius small r will be at a constant distance from this point, which is given by square root of x square plus r square, and it makes an angle theta. Therefore, for any such given point, there will be electric field pointing along this arrow given by dE, which can be split into components dEx and dEy, and since this is theta, this angle will also be theta. Therefore, here dEx will be equals to dE cos theta. Again, we shall be considering only the horizontal components, since the vertical components will cancel out each other. Therefore, by definition, dE will be equals to k dq upon distance square. This distance square, that can be simplified as k dq upon x square plus r square into cos theta. Now, mathematically, cos theta is adjacent by hypotenuse. Therefore, cos theta will be x upon square root of x square plus r square. Substituting that for dEx, we get dEx equals to k dq x upon x square plus r square into square root of x square plus r square. At this point, the first two steps are complete. We have already selected the tiny ring element. We have calculated the electric field only due to this element. So the next step will be integration. But let us first simplify this expression before we integrate it. Now if sigma is surface charge density is defined as charge upon area. Therefore, since we have assumed uniform charge density, therefore sigma will be equals to q upon pi r square, that is surface charge density for the disk, that will be equal to surface charge density for the ring. So that will be dq, charge on the ring upon area of the ring, that will be circumference of the ring into its thickness. Therefore, instead of dq, we shall substitute sigma into 2 pi r dr. The expression for dx that we derived was k dq x upon x square plus r square into square root of x square plus r square. In that, instead of dq, we shall substitute this expression. Therefore, that will be kx upon x square plus r square. Here, these two will multiply to give raise to 3 by 2 multiplied by sigma 2 pi r dr. We shall also simplify for x square plus r square. Therefore, let us assume that x square plus r square equals to z. So, when r equals to 0, that is at the center of the disk, z will be equals to x square, and when r equals to capital R at the edge of the disk, z will be equals to x square plus capital R square. Also, when differentiating, dz will be equals to 2r dr, since the distance from the center of the disk x is constant. So the final expression for dEx becomes pi sigma kx upon z raised to 3 by 2 into dz. Now we shall integrate that from x square to x square plus r square. Here pi, sigma, k, x are all constant. Therefore we shall only integrate for the variable z. The integration of 1 upon z raised to 3 by 2 is nothing but minus 2z raised to minus 1 by 2. Applying the limits, we get 2 pi sigma kx into bracket 1 upon x square raised to 1 by 2 minus 1 upon x square plus r square raised to 1 by 2. This 2 and 2 cancels out. Here instead of k we write 1 upon 4 pi epsilon naught. This expression is just the simplified form. Cancelling out pi, 2, and simplifying this further, we get the final expression for E as sigma upon 2 epsilon naught into bracket 1 minus x upon square root of x square plus r square. This is the expression for electric field due to a disk of radius capital R at a point situated x away from the center of the disk. Can you tell me what will be the electric field of an infinite disk? These are your options. Leave your answers in the comments.